try to be more loud. And if you can't hear me, I can just increase my tone. Alright, today we'll talk about transformer architecture. As in the very first lecture, we will discuss, I will start the presentation by discussing matrix multiplication. So when we multiply two matrices, I'm just reminding you that in order to compute this value, so let's say C11, I have to, let's say, A multiplied by B and B multiplied by A. I have to take the first row of matrix A and the first column of matrix B and take their inner product. So for each element ij, I take the row of A matrix, the ith row, and the jth column from matrix B. The nice thing about matrix multiplication is like really parallelizable. All values we read from different rows and we write to different output values. So these places in memory can be computed and the result can be saved here independently from the other elements. So multiplication is a really parallelizable operation, and even convolutions that we saw in the previous couple of lectures are implemented in the hardware as matrix multiplications. So let's start by natural language. So I'm definitely not an expert on natural language and natural language processing, especially with deep learning, but there are some really fundamental specifics of natural language and in general language that you really need to know, because these are some, yes?
Sorry, could we turn off the front lamps?
Yeah, as long as you don't sleep.
Only the front.
No. Better?
Yeah.
So the really peculiar thing about language, and in general language is text. So the fundamental thing that you need to understand is that words are not discrete symbols. For example, do you remember how we encoded the label names when we want to train a convolutional neural network? What was the representation that we used to encode a word? Nobody? Yeah? Sorry?
It's just to represent labels?
Yes, how did we represent the labels, like the class frog or cat? And
With an integer between the two?
yeah, with an integer, but under the hood was like a one-hot encoding. So given a vocabulary V, we represent each possible word with an index corresponding to 1 in this dimension. So this is like a discrete way to represent language. But when we want to learn semantics, which is meanings between words and sentences, this representation is not a very efficient one because words interact with each other. This is something that may be obvious to some of you because you use your forebrain and have all these top-down influences. But when you want to pass this information in a neural network or anything, this is something that's really non-trivial. And I have some examples on that. So how we interpret a word, even if this word is a verb or a noun, for example, in English we can say, I water the flowers, or I want to drink some water. So So this changes a lot, even what these words mean, even what this word represents. So in this example, the first time it's a verb, and the second time it's a noun. The third thing about languages is that words, okay, we could model language in a character level, but this is really not the optimal way, and this is not how we do it. So let's say I'm trying to have a distinct representation for each word in a language, specifically in a sentence. So given a sentence or a text, we know as humans that language has a lot of non-local interactions. So there may be, I don't know if you ever read like Dostoevsky, there may be a sentence of 100 words where the first one and the 16th one interact with each other. And this is something that by design we cannot do with convolutional neural networks. Do you remember why? Why we cannot model non-local correlations? Yes?
Because we want it to be translation invariant.
No, independent of the invariance, why we cannot, okay, let's say with a single convolutional layer, why we cannot model non-local interactions? So let's say the connect, yes?
Yeah, I think because these neurons have limited field of perception, or
Yes, it's the receptive field for a whole convolutional network, so a series of convolutional layers. But for a single layer, what is the receptive field of a single convolutional layer? Yes?
yeah, the output from the one before, or
No, it's like a number, like or a, yes?
The filter size, the kernel
The
size.
kernel size, exactly. So with one conv layer, we can only see the k nearest pixels in each dimension. So language, we would model language with one-dimensional convolutions. So this is something that we really need to do by definitions, and it's one of the biggest problems before 2017, so before the transformer architecture was invented by Google AI. Nobody knew how to model these long-range interactions that I'm writing here as non-local. And finally, how we combine the meanings, how we compose the semantics. So the semantics in an image is more of the label if we're doing image classification. But when we have natural language, it's the meaning mostly, or the syntax. This kind of stuff can be the semantics. So it's kind of different. So how, like, our perception of the world influences how we understand different words. Here I have two examples. So the first sentence, it's a bit hard to read, I guess. That's the purpose of the example. It said Jack and Jill went. So we read this character as W without even thinking about it. And in the second, it's the poll vote was the last event. So when you read the sentence, you unconsciously think the correct way to disambiguate the sentence. But this is not obvious. And the letter is exactly the same, I think. So meanings interact. When I'm saying that I ate fish yesterday, you're probably thinking of a silver grace fish. But when I tell you I have a pet at home, you're probably thinking something like the image on the left. So this is something really non-trivial and really not solved at the moment. But it's something that the transformer architecture that I will present was able to tackle to some extent. example, in the discrete case, when we want to do image classification, we just map its word that corresponds to the label of the image, for example, dog, into a one-hot encoding. And this is fine, because we want to do image classification. But what about when we have natural language? So there, since words are not discrete symbols, and in general, in all the cases in machine and deep learning where we don't have discrete symbols, we use the so-called embeddings. So no matter if it's like character level embedding, a sentence embedding, a positional embedding, as you will see in the exercise at home, we take all these discrete symbols and map each one symbol from the vocabulary V in a continuous d-dimensional space. So for today's lecture, we will use the D model for this purpose, because this is the symbol that they use in the transformer paper. For example, if I map each word in a 512 dimensional space, this is D model. So wherever you see this symbol D model, you have to think of the D model dimensional space that we are projecting or embedding these words, no matter how many words. So we saw V is the vocabulary. Then I will use the word B, which corresponds obviously to the bad side. And then I use the letter N, where N is the sequence length. Alright. So an ideal embedding space would be structured in such a way that words that have similar meaning are closely together in this d-dimensional space by some metric distance. For example, in a Euclidean space, we can take the cosine similarity. Alright, so far so good. Any questions? Yes?
What was the B again?
B is the bad size. I haven't used, I'm just defining it at the moment. We'll use it later. So you may encounter this word tokenization, since we're talking about transformers in natural language, which is nothing more like the first step in order to create the embeddings. You have to isolate its symbol, in this case its word, and then each word will be mapped to one index in the vocabulary, and each index in the vocabulary will be mapped to one vector in the embedding space. Another critical component we will see during the transform architecture where it is used is the layer normalization, which is fundamentally different from batch normalization, where we saw in what most components are actually using even today. So layer normalization is different. I will draw again this three-dimensional space because this image is meant for comments. So this is B. We said B is the bad size. In ConvNets, we will have here the channels, but here there is no notion of channels. We just have a sequence. So this would be the sequence length, so the sequence dimension. And we will have, this is the embedding dimension, where we call it D model, because it's how they define it in the transformer paper. So instead of spatial dimensions and channels, in the transformers, even in the implementation, you always have to think as a black box that each transformer block, as we will see, each transformer layer, let's say block, will always has an input, a bud size of n sequences of d model dimensions for each element in the sequence. And they also use the word token in natural language. So token and element are both the components of the sequence. So words can, I may be using the word tokens or elements to describe the elements of the sequence. And this is, people use this in interchangeable ways. So, can somebody help me write down the equations for layer normalization? So first let's clarify that this gamma, and beta are trainable components. And then I want to compute this mean and standard deviation based on this illustration that we saw here. I forgot to mention that the difference in transformers and layer normalization is that we don't want to be dependent on the bud size, so we don't take the mean over the bud size in contrast to what we did with bus normalization. So we take the mean in the sequence dimension and in the embedding dimension. That's what these blue boxes are, these blue cubes are meant to be. Any volunteer writing down the equations for taking the mean and standard deviation? All right. No volunteers? Anybody? No? Alright. Another paper, whatever. So this is the index for sequence, this is the index for the model, and this is bud size, it's a vector, bud size, and m is b, and b, divided by d model n.
Sorry,
Yes?
I cannot really see that from here.
All right. Right then. Yeah. Also write 1 divided by model n. This is a bus-wise so this is a vector. Can you read it? And similarly, you can compute the standard deviation. Any questions? Right. Next thing, so we're first inspecting each component individually, and then we will bring everything together. I prefer the strategy. So the next thing we will investigate is the positional encoding. So when we do this tokenization, when we take a sequence and take each word and project it into an embedding, we no longer have a sequence, we have a set. What is the difference between the sequence and a set? Yes?
The set doesn't have the set of the ordering.
Exactly, nice. So we don't have this notion of order, and as we have experimentally found out, this was not so crucial as people used to believe before 2017. So the model like a model who processes word embeddings has no notion of word order, and thus it's permutation invariant, since the process said the order doesn't really matter. So we want to give our model a slight notion of order. Just a quick parenthesis, before 2017, so before the transformer, we used to use recurrent neural networks for these kind of tasks. Even though it's out of the scope of this course, I just want to mention that by design, recurrent neural networks respect the order of the words. So here, when we process a set, we don't have any, by design, respect towards the order of the words. So the cheap solution is to give like a slight notion of order, as I said. So they derive this really tricky and nice trick, which is positional encoding. I don't know where they invent, like how they end up thinking about it, although it's a nice strategy. So each one of these dimensions, so in the transformer paper that you will read to do this homework, this B model dimension is 512, so it means that each word is mapped in the 512 dimensional space. So each one of these dimensions, which is indexed by the index I, so I is the dimension index, so it goes from 0 to 256 in this example, so B model divided by 2. The only reason that it doesn't go to 512 is that we want to have to index differently the even and odd values. So there are two things changing. So the positional encoding is a matrix. So in this dimension we have the sequence length, and in this dimension we have the model. So each of the dimensions will be slightly altered, and each of the sequence will be slightly altered. So the index that determines how differently the sequence will be altered is I. No, I is for here. So the index for I determines how the embedding dimensions will be differently modified. And the index for the sequence is position. So from 0 to the maximum sequence length. So we vary both of them in practice. There is no theoretical justification as to why do we do this. So if we were to apply this as you were doing the exercise, you will implement this yourself. So let's see. What is the wavelength of this equation? And let's say the top one. Yes?
So in general, 2 pi, or what do you mean?
All the thing that's on the sign, what is the wavelength? So when we have sine of I don't know, this would be the k position. 2 pi divided by lambda. And here we have 1 divided by 10,000, 2y. 256, what does happen? What is it happening in the wavelength? Is the wavelength increased or decreased? Yes?
The wavelength is increasing. It starts from 2 pi and goes to 2 pi times 10,000.
Perfect. Yes. So that's the point. So here I have some kind of random sinusoidal wavelengths or frequencies. It's the same. So here actually when I goes to 2, I'm not drawing I equals 1 because then I have to switch from sine to cosine. So I'm going from I equals 0 to I equals 2. So, so here the wavelength is shown to be 2 i's as the previous one, but in practice it's 4 times, because they didn't have a lot of space to draw. And then for I equals 4, because it's 2i, 2 times I, so this is like 8 times the initial, let's say. But the concept is exactly what you said, that the wavelength is increased. And what does this x-axis indicate? Can somebody guess?
The position.
Yes. So it goes from 0 to sequence length. So the pulse index that they use here. So we have 3 different things happening at the same time. For odd and even indices of I, we use a different sine and cosine. So we are altering between dimensions from sine to cosine. Second, we have a different wavelength. And third, each element in the sequence gets a different value of this sine or cosine in this respective dimension. I know it's a lot, but any questions? Alright, so you have to implement that in the exercise. Alright, so far we took the word, we tokenized this sentence in words and project them as a word embeddings. We add some positional encodings. So what's next? Next, it's finally the time to inspect the key component of the transformer architecture, which is the attention, and specifically self-attention. Why we call it self-attention? Because it's how we attend to different elements in our data, and our data is a sequence. So how we attend to different tokens or elements in the same sequence. And before that, a very, very helpful illustration or concept that was introduced surprisingly came from an idea from the 90s of information retrieval systems. So in information retrieval systems, there is this idea of the keys, the queries, and the values. This is like a rough analogy, so don't take everything absolutely absolute. So the query in a database is what we are basically trying to find. The key in a database, it's basically how this query maps to the different components of the database. What does this database may contain? For example, we can search for YouTube videos based on the title, while the title and the content have like distinct representations. The title is just the text, but we actually want to see the video that corresponds to this title. So the actual video is more the values of the database. And this can be found in the literature of the 90s as a content-based lookup. So what's the most important here? The most important thing here is that this keys, queries, and values are three distinct representations. We want to have a different representation basically. So query is what we are trying to find, and keys and values are two distinct representations of our database. So basically keys is what is possibly shows an indication on where to look, and values is the content that we're actually interested in with this query. Any questions here? All right. So here is self-attention. Let's start with an example. We have an input sequence. So in this example, we have 4 elements. So n equals 4, and b model equals 6, I think. So we start off by taking 3 distinct linear projections that will be traceable, but for the moment it's just 3 different linear projections defined as Q, K, and B. So for that we just have like a weight matrix. Subscript. So these 3 are linear projections that will be optimized via backpropagation, and we will end up, at least for self-attention, we will end up with 3 different representations of the same input sequence. So this is a sentence in natural language. It can be, we can make a more general something like any sort of sequence, but let's say we're staying in language for now. We have 3 different linear projections that correspond to the same sequence. Then we apply the famous formula that's on the presentation, on the slide. Okay, we'll go in the saves in a bit. So these are matrix multiplications. What is the save of Q? Yes?
Should be backside times.
Yeah, let's say it's expanding on the bud size, so I will not write the bud size dimension. Yes, bud size times?
Expansion, not. Well, what do you mean expanded on the backside? So.
I mean, I will not. Okay, let's write bud size. I mean, let's.
Oh, right. Okay.
I mean, the matrix multiplication is not happening in this dimension. Okay, let's write bud size.
No.
Okay. So basically, the last dimension will be multiplied here. So this dimension will change. So this dimension remains intact. So let's say here the doesn't need to be a square matrix. We can make a linear projection in whatever dimension we want to. And Q, K and V follow the same principle. So I'm just ignoring the bad side. For simplicity. Okay. Any question regarding this one? Yes?
Why N and why not E model? Should it match the last dimension of like X?
Because when we have two matrices, the last dimension is multiplied with the.
First dimension, yeah. The last dimension is D model, is these two.
Yeah, we take the model,
Yeah.
so this
That
dimension
has to match.
is where, yes, I didn't say, this is the sake of Q, it's not the sake of W.
Oh.
The sake of W,
Oh yeah, yeah, sure. So
no problem, is the model times the Q. Right? And I'm not writing down, but similarly for these ones. So we'll simplify a little bit, and we use dk for all values. So we use dk equals dq equals dt. So we'll just use dk from now on. So dk is a dimension where we linearly project the input sequence or set variable. Alright. Then this answers the question why we need a transpose here. So if we want to multiply these matrices, we have to transpose one of them. And the multiplication happens in this dk dimension. Right? So what is the sake or we all was it's bad sign, maybe whatever. What is the sake? What is the sake of this matrix? Yes?
N times N.
Perfect. Is it clear why the sake is n times n? Alright. So this is almost the attention matrix. So we have our sequence, we take these linear projections, we apply this formula. Alright. So this slide will have illustration. So what is happening is that all the elements of the sequence that respond to the queries are multiplied here. And since we are on a, let's say, this inner product is a measure of similarity. So we weigh how much the elements of Q, the queries, correspond to K. The beautiful part is that this is happening with the matrix multiplications in parallel for all the words in a sentence. So I also have an illustration that shows, this is an illustration that shows it only for one word, one token. So that's why they use a non-capital letter Q, K, and V. So what is happening in this formula that you see, this is nothing but the softmax. So this Li is basically for one individual word for word embedding of interest. So this embedding of beetle, this E is the embedding. So for each word, we take the similarity of the query, the projection of this word, with all the other words. And with this multiplication, we do this for all the queries in parallel. So if we just see for one word of reference, so this beetle, you see that in the denominator we have Q multiplied by Ki. I think it's missing here. So in a vector form, I'll use index J here to avoid confusion. So this is index I. So this is the weight or the attention, whatever. You can use whatever letter you prefer. So we find the similarity or the agreement between all the queries with respect to all the other. So this is the multiplication of this, the Q of this specific embedding with this specific K, but this is not enough. We want to see how relevant the word is relative to all the other words. So this is nothing, if you remove this is nothing but the weighted mean. So we take a weighted mean to compare the similarity of all the different queries and values. So basically, this n-square matrix, we said this n-square matrix, each element in this square matrix indicates the similarity between index I and J in this, of the similarity of all the possible combination of the tokens in the sequence. It's not the similarity of the tokens, it's the similarity of all the tokens with all the tokens. So it's like quadratic, also the complexity is quadratic. So it's like all the pairs. So we consider at each computational step, so at each module, we already consider all the pairs and the possible combinations of the pairs in the sequence and weight them together. So there's a very strong assumption that we can do that. Can somebody imagine the assumption from the beginning? Like, what am I assuming that is given for a sequence? Okay, maybe it's a little hard to get, so we have clarified in the beginning. So we assume that all these elements of the sequence are known in advance. So for example, if we want to predict the next element of in a real life scenario, an online application where the values are not known in advance, we cannot apply the transformer. But this is widely applicable in natural language processing. We already have all the text and the corpus and the sequences and the sentences in advance. So this is really important. So I want to emphasize that this softmax, which apart from the exponentiation, it's a weighted average. So this weighted average is really important. I mean, we cannot disregard the order. Maybe one would say, why we don't multiply these matrices first and then with Q. No, this is not important because we want to weight each query of the same word, like with respect to all the other. And I have a nice illustration of that here. So the query is shown on the left side of the image. So So the first matrix multiplication is the queries with the values, the same way that we began the lecture. So each element, this A11, corresponds to the similarity between query 1 and key 1. Is that clear? That's why we say that everything is happening in parallel already from the matrix multiplication. So it's a highly parallelizable module. Next, in this attention matrix, which I'm showing, I'm not showing the softmax, but basically the softmax is applied row-wise. So after we find these similarities, it's not a sufficient indication. We have all the pairs, but we want to see how all these different pairs weight the query, which is Q1. So that's why we apply softmax in this row, and this O11 shows us, okay, it's already multiplied by the output value, but by taking the softmax in each row, we are already weighting the query with all the possible keys. So it's already seeing the whole sequence. So it's a highly global operation. That's the point. And then in the second matrix multiplication, we take this n by n and we multiply it with v. So what would be the final output of when we multiply this n by n matrix with v? What do we get? Right, n times dk, because it's dv, but we said that we use the same embedding dimension for key squares and values. So this is the output of the softmax. And of course there's the bat size dimension, everything happens. But for all the sequences in the bat. Alright. It's probably a lot. Any questions so far? So if we were to draw a black box so far, maybe one question. What is the purpose of this thing? Have we discussed that? No? Okay. Is it clear what's happening? That we scale down element-wise everything by dk? Okay, I guess this is clear. So basically we have this n by n matrix and we scale all its elements by the square root of dk. So dk, let's say in the transformer paper, is something like 64. So why do we need to scale down all the values? Any ideas? So in this figure, let's say that here the embedding dimension is 3, which doesn't seem to create problems, but all the time I'm repeating that deep learning is all about scaling. So what if the embedding dimension, this 3, this dk dimension, what if this dk dimension was not 3, but 64, as it is in the actual transformer paper, or in the recent ChatGPT, whatever papers, like even higher, maybe 128, maybe 256. What would happen if we take Q1 and K1 and multiply them together? So we take their inner product. So as I'm showing here with the blue and red arrow. So this inner product would get a really high value. And this is a problem. Why? Because we want to apply softmax, and softmax looks something like this. From 0 to 1. Yeah. From 0 to 1. So this is how softmax look in each individual dimension. So what happens if we take this, if this inner product gets very large, we might end up in these saturating areas of the softmax. Or, if you'd like, if all these values are in this range, because they get really large, or their magnitude gets large, when we apply softmax, we will not see any difference, like all the values like all these different values in the x-axis would be the same. So it will look like a step function, more or less. So we will only have outputs in the minus infinity and plus infinity. So this, they observed, like the authors observed, that this makes things really unstable. And thus they decided to divide by this value. Actually, they provide some mathematical indication as to why it is the case, which I thought is helpful for you. So the indication says that we assume, so in this example, these Q1 and K1, let's emphasize on these two. So Q1, K1. So let's assume that these are independent random variables with mean of 0 and variance equals to 1. So assuming that, we can see that when we take the product, so this is the thing that is problematic and gets unstable, this inner product. So we divide by dk. So if these are two random variables, we can treat their inner product as random variables. And they say, they argue in the paper, that the expected value of these so to simplify things, I've written down here that you can take the expectations inside or you can take the sum outside, whatever. And these are, since these values are independent, this is our assumption, we can apply the expectation in each one separately. So the resulting mean of the sum is 0, which is not a problem. Are you able to follow why the expected value here is 0? Any questions? Yes? So if we assume that these vectors, so each element in this vector, so we said that this dimensionality is dk. So we assume that each element in this vector has a mean of 0 and variance of 1. So E Q1 equals 0 and var Q1 equals 1. So this is the assumption that we have just random values basically, without assuming any distribution. We don't assume that these follow a normal distribution. We just assume that they are independent random variables with mean of 0 and variance 1. And we are interested in basically the mean and the variance of their inner product. Is that clear? So if we take the expected value, basically the mean, we can just swap the expectation with the sum. And then, since these values are independent, we can apply the expectation in each one separately. But we know that this one is 0 and this one is 0. Is it clear? And for the variance, we use this formula from statistics or mathematics in general. I will swap the sum immediately. Expected value Q1, K1, and then square. So this is this one here. And the expected value is already computed to be 0. So I'm not repeating that. Alright? And then, basically, you apply these in these terms specifically, and then you take it out of the exponent, so you get that. So basically, sorry, this is var, so this is still variance. Circular. No. Variance, expected value. No, expected. Expected value. So this is expected value. Okay. Q1 square. Times expected value A1. Okay, I'm missing some part. I have to look it up. But I want to emphasize that if you follow this equation, you get this one. Variance Q square variance of K square. And we know that this variance is already 1. So it's sum of 1 from 1 to dk. So the variance is dk. So basically all this analysis is just to prove something that they just write it down in the transformer paper, that the variance of this inner product is dk. And as dk increases, we can have really large values for the numbers here in this attention matrix. Is that clear? Alright.
Okay, sorry for interrupting, but the I don't know if it's recording, it shows like low battery something. So maybe you want to stop it, or so that it's at least.
Oh, okay. I think it will last 20 more minutes or so.
So sorry.
No problem.
So the
this single-headed tension or self-tension without any additional, where the output is bulk size times n times dk in general. So if we set dk to d model, we have the same save in the input and the output, which would be the exact case if we use the computations as we have pre-described them. However, they found out that even though everything here is happening in parallel, we can introduce another way of parallelism, which applying this operation multiple times. So instead of taking the x and have only one value, only one triplet of queries, keys, and values, we have multiple of these triplets, and we call them heads. And this operation is completely parallelizable. So this is the second parallelizable, let's say, component. So we have multiple heads, but however, we have 8 heads that define 8. So it is an integer referring to the number of heads. So how could we make this operation? How do we pick? So we have the model, we have 8, and we have dk. So how can we make this operation to have a similar cost with a single head operation, the similar computational cost? How can we define the heads in the dk dimension so